Secretary General of the United Nations, I send greetings on behalf of the people of our planet. We step out of our solar system into the universe seeking only peace and friendship, to teach if we are called upon, to be taught if we are fortunate.
Oiknis poteste khairete.
Hola y saludos a todos. धरती के वासियों की ओर से नमस्कार.
We know full well that our planet and all its inhabitants are but a small part of this immense universe that surrounds us, and it is with humility and hope that we take this step.
各位好嗎？祝各位平安、健康、快樂。
Shalom.
Bonjour tout le monde. تحياتنا للأصدقاء في النجوم.
Hartelijke groeten aan iedereen.
Konnichiwa. O genki desu ka?
Tanti auguri e saluti.
Namaskar. Bishe Shanti Hok.
สวัสดีค่ะสหายในธรณีโพ้นพวกเราในธรณีนี้ขอส่งมิตรจิตมาถึงท่านทุกคน
Herzliche Grüße an alle.
Paz e felicidade a todos.
Hello from the children of planet Earth.
Earth, for as long as we have records for most peoples, was the center of all things. For the peoples of Western Europe, this understanding had been established by such authorities as Aristotle. By official doctrine, around the earth revolved the sun, the moon, the planets, the stars, and all the rest of the heavens. As set down in the 2nd century AD by Ptolemy, this view prevailed for over 15 centuries. Then, in 1543, Nicholas Copernicus suggested an arrangement that placed the sun at the center of creation. Earth was but one of several planets that moved around it. It was the Italian scientist Galileo who confirmed this revolutionary understanding by using a newly invented instrument, the telescope. He carefully recorded his observations.
On the 7th day of January in this present year 1610, at the first hour of night, Jupiter presented itself to me. Beside the planet there were 3 starlets, small indeed, but very bright. Returning on January 8th, I found a very different arrangement. On the 13th of January, 4 stars were seen by me for the first time.
Galileo argued that his observations proved the new system.
Here we have a fine and elegant argument for quieting the doubts of those who are mightily disturbed to have the moon alone revolve about the earth. Our own eyes show us 4 stars which wander around Jupiter.
But a new understanding of the universe was seen as dangerous. The church put Galileo on trial, and he was made to recant what his eyes had seen. But in Renaissance Europe, Galileo's ideas could not be suppressed. Others, like Johannes Kepler, enthusiastically embraced the new view. Kepler worked out a new celestial mechanics. Excited by the new universe, he wrote Galileo,
"Let us create vessels and sails adjusted to the heavenly ether, and there will be plenty of people unafraid of the empty ways. In the meantime, we shall prepare for the brave sky travelers maps of the celestial bodies. I shall do it for the moon, you, Galileo, for Jupiter."
3.5 centuries later, Kepler's vision had begun to be realized. All the solar system he knew had been visited.
We're interested in how the Earth fits in to our solar system, how it fits into the universe. The general principles that govern the kinds of things that have happened in the past on the Earth and that will happen in the future can be illuminated by looking at these other systems.
We know today that the Earth is one of 9 planets circling the Sun, that together with the Moon, our place in the solar system is among the inner planets close to the Sun. These planets are small, dense, and rocky.
Mercury is the innermost planet, and it looks very much like the Moon. It has no atmosphere and many impact craters, some volcanic activity, but it's dominated by these very early primitive processes. Venus is the next planet, and it was masked entirely by its atmosphere. But then we've recently been using radar to to look at its surface. It's a close twin to the Earth in size and in density, but it seems to have evolved quite differently. Our next neighbor is Mars. It's been of great interest because it's been the subject of so much science fiction interest. We early thought it was a very primitive planet, but it turned out to be much more complicated when we got a close look. It has enormous volcanoes, the biggest ones in the solar system. It has great canyons and stream valleys. And water can't flow on Mars under the present climatic conditions. So it says that in the past, Mars has had vastly different climates to the way it is on Mars right now. These stream channels say that water flowed on the surface, and that enhanced our possibilities of finding life. But when we landed on Mars with Viking, we could find no trace of organic matter.
Pioneer 10 and 11 were the first spacecraft to travel beyond Mars to the outer planets, Jupiter and Saturn. Each Pioneer carries a plaque, a kind of license plate, for ultimately they will leave the solar system and travel among the stars. Pioneer sent back our first close-up pictures from the outer planets, of Jupiter and its red spot, of Saturn and its rings. Once every 175 years, the planets line up in such a way that a spacecraft from Earth can visit each of the outer planets in turn. Not only Jupiter and Saturn, but also Uranus and Neptune. A grand tour. That special opportunity came in 1977. 2 spacecraft were planned, one to make the whole tour, the other to leave the solar system after Saturn. This was to be the Voyager project.
The Voyager mission was designed to study the giant outer planets, which represent a rather different population of planets than the inner planets that we're used to, one of which we live on. We had several principal areas of investigation. We wanted to study the atmosphere of these giant planets. We wanted to study the satellite systems of these giant planets. We wanted to study the magnetic field structures, which are quite immense. And then finally, we wanted to study the ring systems of these planets.
Late summer of 1977, the 2 Voyagers lift off. And on board, a message.
As the Secretary General of the United Nations, who represent almost all of the human inhabitants of the planet Earth, I send greetings.
John Cassani was the Voyager project manager, and he realized that there would be an opportunity to send a message with Voyager as had been done with the Pioneer mission. But here was an opportunity to do something more than a license plate, something which would have a lot more bits, a lot more information about us. He contacted Carl Sagan, and Carl Sagan and Frank Drake discussed the possibility of putting a record on board Voyager, a very economical way to send a lot of information. Here in scientific language are the instructions for play for the record, and this particular symbol here is the first picture that the extraterrestrials would see, a simple circle to indicate that they were playing it correctly. The record would contain 2 hours of sound, including 118 pictures of life on Earth, as well as 90 minutes of the world's music, greetings from the people of the Earth in 60 of the most populous human languages, as well as greetings from the President of the United States and the United Nations.
Voyager program is really part of man's interest in exploring his surroundings. Really, it, in a sense, started with Galileo in 1610 when he combined what at that time was advanced technology, his 8-power telescope, with skilled scientific observation, and of course his discoveries had a very significant impact on his contemporary society. Voyager continues that tradition in the sense that it also combines advanced technology with skilled scientific observation.
Galileo wrote,
I succeeded in constructing for myself so excellent an instrument. Perhaps other things, still more remarkable, will in time be discovered by me or by other observers with the aid of such an instrument.
The scientific data of Voyager are sensed by these sophisticated sensors, and especially this long focal-length camera here, which is capable of seeing detail in almost as much clarity as a large telescope on the Earth, for example, looking at the moon. Here is really 3 large computers that sense its orientation, remember commands that have been transmitted up as much as a year beforehand. The way that the spacecraft is powered, since it's moving out away from the sun, beyond Mars, through Jupiter's system, beyond that to Saturn, and beyond Saturn, is with nuclear batteries, not with solar cells. These nuclear batteries, which are on this large boom here, are powered by plutonium, which produces heat. The heat is then used to drive, in effect, large thermocouples, which produce the electrical power steadily to power the spacecraft. The large antenna here beams the radio signals to Earth, where one of 3 large antennas on the Earth receives the signals and transmits them back to JPL.
The antenna is tracking Voyager 2 spacecraft, which is about 500 million miles from Earth. The spacecraft is transmitting at about the power of a 20-watt light bulb, and we are receiving television pictures from the planet and the spacecraft at this time.
Mission control at JPL, the Jet Propulsion Laboratory in Pasadena, California. The 20-watt signals from Voyager are relayed here. From Saturn, it takes almost an hour and a half. How Voyager is working is checked, and new programs are sent back to correct or change commands. On board are 10 separate data-gathering instruments. The data comes back in digital form, binary dots and dashes transmitted at high speed. Much of the data is reconstructed to form pictures. Each picture is made up of 640,000 dots, and each dot is numbered as to how bright or dark it is. Each scene, photographed through a different colored filter, can be reassembled into a single color picture of remarkable clarity. By computer manipulating the numbers, the pictures can be enhanced and modified. Voyager's astronavigators must anticipate everything in advance and must make onboard programs to meet every contingency because of the time delay in sending and receiving information. Jupiter. In Western mythology, the father of the gods. For Galileo, it provided a proof of the Copernican system. For later observers, it has been and remains an object of awesome majesty and mystery. And as it holds so much of the early material of the solar system, it could help explain the origin of life. Jupiter is truly immense. 11 Earths can fit side by side across its diameter, and more than 1,000 Earths fit into its entire volume. Aside from the Sun, Jupiter contains twice as much material as the entire solar system. We see only Jupiter's outer surface marked by these bands and zones. Jupiter is not solid. It is made of hydrogen and helium gas. Underneath is an immensely deep ocean of compressed hydrogen, which behaves like liquid metal. Only perhaps at the very center is there a small rocky core, rather larger than the Earth. And the interior is still hot from the planet's formation 4.5 billion years ago. Perhaps the most intriguing thing about Jupiter is its red spot. The astronomer Giovanni Cassini first recorded it in his notebooks in 1665. This 19th century sketch of Jupiter shows the spot. It's as large as 2 Earths. What is it? Why is it red? And how can it have lasted for over 300 years? Normally, as in this experiment, when two materials, liquid or gas, flow past each other, they become intermixed. Yet this does not seem to happen with the red spot, or with Jupiter's belts and zones.
In fact, what we see are these different islands of color which persist sometimes for hundreds of years. And this is a very amazing thing and very difficult to explain. Why should these fluid features exist for so long in the presence of all this turbulence, really? The movie here shows pictures of Jupiter taken once every time the red spot was beneath the spacecraft. That means every 10 hours the shutter was snapped. Then this is played in a sequence over and over again so you can see motion. Look to the west of the red spot, you can see this turbulent, rapidly mixing region. You can see rapid flow to the east at the equator. Just above the equator you can see another turbulent region. And this rapid mixing makes the existence of permanent, different colored, different chemical features even more mysterious. For instance, some of these features like the red spot and the belts and zones and some of the ovals have lasted for decades or even hundreds of years in spite of all this rapid mixing. This movie shows motion around the red spot. You can see, for instance, spots coming over the top of the red spot, some going off to the west, some going off to the east. You can see this very turbulent region to the west of the red spot. You can see a flow down below the red spot that actually changes, reverses direction. You can see little turbulent regions around the spots farther to the south that resembles the pattern around the red spot, but at reduced scale. Again, the existence of this very turbulent region so close to such a permanent weather feature as the red spot is very hard for me to understand.
Before Voyager, the red spot, seen here computer-enhanced, was thought to be a vast rotating storm like this hurricane on Earth. But now one theory being considered is that the red spot is a kind of solitary wave.
Solitary wave is a wave in which the tendency of the wave to flatten out because it's higher than its surroundings is exactly balanced by its tendency to break, rather like the waves on a beach break. Since we can't do exact experiments on the red spot in the laboratory, we are now looking at an analog flow. And I'll show you this analog experiment. What we have are two layers of fluid. One is a heavy layer of salt water, and above it is a light layer of fresh water. And I'm going to mix up this fluid in this section right here. And when I mix up the fluid in the tank and pull out the barrier, you'll see this solitary wave develop in the flow. And this is our analog, if you wish, of the red spot.
To know exactly what the red spot is and how it functions, we'll have to wait for a more complete understanding of the Jovian or Jupiter's atmosphere and its weather. Our weather is divided into distinct hot and cold zones by the jet stream.
One of the most exciting things that have come out of the Voyager mission is that the Earth and Jupiter are very similar in terms of their weather systems. In the case of the Earth, we have the situation that our weather is driven by the sun's heating, which has this difference in temperature between the equator and the pole. Now on Jupiter, this is different. The sun is very much weaker, and the temperature at the equator and the pole are roughly the same. And of course, there is a further additional source of energy, namely internal heating. So that gives you initially a difference. But where the similarity comes in are these belts and zones, which we believe are like high-pressure and low-pressure systems stretched out around the planet due to its huge rotation, and within them are very small differences in temperature.
This computer model was actually developed for the Earth's weather system. But when information about Jupiter was put in, the model began to develop the distinctive appearance of that planet. Large Earth features like the jet stream become the more narrow and horizontal bands and zones found on Jupiter. Some scientists, however, see the Jovian weather system to be the result of Jupiter's differences from the Earth.
One of the differences between Jupiter weather and the Earth is that the atmosphere of Jupiter is continuous with a fluid interior, and also there's an internal heat source on Jupiter and not on the Earth. Now, Professor Busa of UCLA has a laboratory experiment where he takes a spherical container, puts it on a rotating platform, and heats it from within. Naturally, convection currents form, but because of the rotation, these currents are arranged in long, thin columns. Some of us think that this is what's going on Jupiter, and that this difference between Jupiter and the Earth is very important for understanding Jupiter weather.
Jupiter's weather takes place in an atmosphere rich in the materials thought to have made up the early solar system, especially such compounds as methane and ammonia. Could the conditions in the Jovian atmosphere today be the same as those on the early Earth when life began?
One of the primary goals of this laboratory is the search for the beginnings of life. We want to find out whether organic matter can be synthesized under conditions that exist today in the Jovian atmosphere, or as a matter of fact, in the atmosphere of Saturn, or one of the satellites. Here in this flask, we have a mixture of methane and ammonia. Methane gives us a source of carbon. The ammonia gives us a source of nitrogen. The carbon and nitrogen are important in the formation of organic molecules. There's a spark going through there. Now, this spark represents for us the electrical discharges, the storms that may be taking place in the Jovian atmosphere. Up to recently, when experiments of this type were done, some people doubted the presence of electrical discharges in a Jovian atmosphere. But today we have direct evidence from the Voyager photographs of the presence of ball lightning, for example, of the aurora, which clearly establishes that lightning as a form of energy is something which is indeed present in a Jovian atmosphere. What happens then when we pass an electrical discharge through that mixture of methane and ammonia? Organic matter is formed. So what we see happening in the Jovian atmosphere today may have taken place on the Earth's atmosphere, say, 4.5 billion years ago.
Geneticist and life scientist Dr. Norman Horowitz.
The abundant life that we see all around us on the Earth is made possible by the Earth's peculiar environment, which may well be unique in the solar system. The Earth not only has a temperature which is compatible with the production and existence of complex organic compounds, it also retains a dense atmosphere of the elements of which life is composed, and in addition, it has a large amount of liquid water, the ocean. The ocean is probably the place in which life originated on the Earth.
There's no question that the building blocks of life can be made by many ways. And if we can do it in a laboratory, presumably it must happen elsewhere, it must happen in planetary atmospheres, on planetary surfaces, and so on. But we must have some mechanism by which these molecules can be brought together. They have to interact. And I believe that the single necessary ingredient for such an interaction is liquid water. So if we can find liquid water somewhere in the universe, I think we may be able to conclude that there is also life there.
At certain depths, the Jovian atmosphere does hold water. And since there is energy and the organic building blocks are abundant, shouldn't the chances be good for life?
The problem with Jupiter is that Jupiter contains a heat source deep inside its great atmosphere. And Jupiter actually produces twice as much heat as it receives from the sun. As a result of this fact, the atmosphere of Jupiter is in constant convection. Gases are forced from the deep interior up into the upper atmosphere, and they circulate back down. The result of this is that any organic substances formed in the upper atmosphere of Jupiter are carried down in these great convective cycles into the deep interior, where temperatures get as high as 10,000 degrees absolute. And there the compounds are destroyed by heat. The result is that there's no chance for the evolution in the Jovian atmosphere of the kinds of complex organic substances that we think are necessary for an origin of life.
During its brief encounter with Jupiter, Voyager wasn't able to prove Dr. Horowitz right or wrong. In addition to Jupiter, Voyager also studied its major moons, the 4 satellites Galileo first saw. This is computer-drawn film of Voyager passing the outermost moon, Callisto. Then come Ganymede and Europa, and finally, Io. These were the best views available of any of Jupiter's moons before Voyager. 13 had been discovered, but virtually nothing was known about them.
In the case of the satellite systems, we have a miniature solar system about Jupiter, the 2 inner satellites, Io and Europa, being dense, rocky objects like our own moon, the 2 outer satellites, Ganymede and Callisto, being Mercury-sized, but being half water ice. So we expected to see rather unusual objects, and in fact, we did see unusual objects.
Callisto, outermost of the Galilean satellites. It's about twice the size of the Earth's moon. Callisto is half made of ice. Under a frozen ocean hundreds of miles deep is a rocky core. Its surface is intensely cratered. In some places, gigantic impacts seem to have turned the ice to slush before it refroze. This computer-enhanced picture shows that Callisto's surface is saturated with craters. Why? The solar system condensed from a huge disk of primordial matter swirling around the sun. The condensation is thought to have happened about 4.5 billion years ago. The planets and moons emerged from the disk by gathering up smaller objects in the solar system, meteors, asteroids, and comets, through an intense bombardment that lasted millions of years. The bombardment left their surfaces scarred with impact craters.
This is Meteor Crater, Arizona. It's one of the rare impact craters we find on the Earth. There are, of course, many, many other craters that have been formed on the Earth and have been either eroded away or covered up by sediments. And it's only the youngest that are preserved, such as this one, which was formed about 25,000 years ago. Now, we're interested in these craters primarily because it provides us a tool for dating surfaces on the other planets and on the Galilean satellites of Jupiter. To find a surface that is chock full of craters, we must be looking at a surface that is very ancient. In fact, we must be going back to that point in time in which the rate of cratering was much higher than it is today, a time in which the pieces from which the planets themselves were built were still being swept out of the region around the planets.
And so we see here on Callisto an actual record of the last stages of planet formation. From Callisto inwards to the largest moon in the Jupiter system, Ganymede. Somewhat bigger than Callisto, Ganymede too is half made of ice. Much of Ganymede's surface looks as if whole chunks of Callisto had been grafted on. But the rest of Ganymede's surface is quite different and unique. It is covered with grooves, strange parallel lines twisting over the surface.
able to see here are what geologists call superposition patterns, places where one geological structure or feature is on top of another one, indicating that it's younger. Here we have two different sets of groove patterns, this groove pattern crossing over and apparently lying on top of this older groove pattern. We have then several sets of craters, some craters which have been destroyed by this younger set of grooves, other craters which have been laid down on top of the younger grooves. Making craters that large is a very improbable event in today's solar system. So again, we believe that these processes were going on while heavy cratering was occurring, which to planetary geologists means early in solar system history.
So the grooves must be very old, almost as old as Ganymede itself. As the ice froze, it stretched apart, making a depression or groove. This kind of faulting can be found in the western United States.
And in fact, rather close to us here in Flagstaff, Arizona, there is a beautiful groove that has just about the size and shape of many of the grooves on Ganymede. In this case, we know in the western United States the groove is formed by extension or tensional pulling apart of the crust of the Earth, and we think that that's what is the principal cause of the formation of grooves on Ganymede.
The grooves have recorded unusual events on Ganymede. Here they have been displaced. Is this an earthquake fault, like the San Andreas Fault in California? If so, Ganymede is the only place in the solar system besides the Earth where such faults have been detected. But Ganymede, like Callisto, is a dead world, a museum of its own early history. From Ganymede inwards to Europa. Europa is the size of Earth's moon. A frozen ocean slightly deeper than the Earth surrounds a large rocky core. But unlike Callisto and Ganymede, Europa is almost perfectly smooth, like a billiard ball. Its only distinguishing feature is that the surface is covered with cracks.
Unlike Ganymede and Callisto, in which we see dense populations of impact craters on the icy surfaces, on the icy surface of Europa, we see virtually no impact record. We see 3 impact craters about 20 kilometers in diameter, but this is a very, very small population compared to the other 2 objects. Evidently, Europa had to remain young and active beyond the period of the torrential bombardment, so that its surface was continually being renewed. Instead, what we see are a complex network of intersecting dark bands, and they're thought to have resulted from the expansion of Europa as the ocean froze.
The cracks on Europa can hardly be distinguished from the cracks seen in polar regions on Earth. This is the ice of Antarctica, seen from space. And this, Europa. There is a color difference. Perhaps Europa's ice is contaminated with pulverized rock. What Callisto, Ganymede, and Europa show is a record of the natural history of a planet or moon. It is formed by meteor bombardment. As aeons pass, part or all of the older cratered surface may be covered over or erased with new landforms. Even this new surface becomes lightly cratered by the remaining debris. So the differences between Europa, Ganymede, and Callisto are probably the result of when the oceans froze. On Europa, the meteorite splashed down into a liquid sea, which froze only afterward, so there are virtually no impact craters. On Ganymede, the ocean froze at about the same time the bombardment was lessening, erasing some of the original cratered surface with grooves. But on Callisto, the ocean must have frozen before the end of the bombardment, leaving the surface a reliquary of the violent birth of the solar system. If Jupiter's moons did develop this way, Europa could possibly have life. Its early ocean must have been liquid for millions of years, possibly long enough for life to begin. So if there is liquid water today underneath its completely frozen surface, life that may have once started might still remain, living like these newly discovered sea worms on Earth in total darkness. From Europa inwards toward Io.
I think it's fair to say that one of our biggest surprises with Voyager was Io, the innermost of the Galilean satellites. And it was really rather hard to surprise us with Io. We already knew enough about it to know that it was one of the more bizarre objects in the solar system, but even so it managed to astound us when we actually got there.
Io is the size of the Earth's moon, but its surface is unlike anything ever seen before. This cratered surface was the stage for the most unexpected discovery of the Voyager mission.
I was doing my job of optical navigation and looking at pictures of the satellites of Jupiter and stars to tell us where the spacecraft was. I expected to see the satellite Io and 2 stars in the frame. I noticed the appearance right off the limb of Io of an anomalous crescent. And my first impression was that this crescent was another satellite behind Io. By analyzing trajectory geometry printouts of what objects might appear in this frame with Io, it was determined that no known satellite would appear in this frame with Io at that time. My next thought was that, well, this was perhaps a newly discovered satellite, but at this distance, this object would be too large and too bright to not have been discovered before from the Earth. I contacted a camera expert who informed me that no known quality of the camera could induce the appearance of this anomaly. Therefore, the only alternative that was left in discovering what this anomaly was that it in fact did have something to do with the satellite Io. I have determined the latitude and longitude in the region of this crescent on the surface of Io. This turned out to be the latitude and longitude of a large heart-shaped feature on Io, already known to be a volcanic feature, but of course not ever believed to have been an active volcano. I concluded that what we were definitely witnessing was an active volcanic eruption, and that the crescent itself was a volcanic plume, a dust cloud of gas, an actual volcanic eruption, the first ever witnessed on a body other than the Earth in our solar system. The other bright spot down there is also another volcanic eruption. What we are observing here in the Discovery frame was in fact 2 simultaneous volcanic eruptions. The surface of Io is incredibly active, much more active volcanically than even the Earth.
We found out that not only was Io's surface being modified by volcanic processes, it was being done so literally in front of our eyes. There were active volcanoes going off at the time we were there with Voyager 1, at least 7 or 8, perhaps 9, clearly identified explosive volcanic eruptions throwing materials hundreds of kilometers above Io's surface in the force of the eruptions. This picture shows 2 different volcanoes which are seen from several different angles to give some perspective. Here we see ejecta coming out from the center of the volcano falling back down to the surface. Here we see it lit against black sky, so that the symmetrical form of the eruption, much like a sprinkler head, and that's throwing material up approximately 70, 80 kilometers in that view. Io shows us nearly the full range of volcanic-type landforms, and in this picture, very prominently displayed are at least 2 calderas, volcanic depressions, with what look like lava flows spreading out from them. It also shows several diffuse features, which look like they may have been something more explosive, like the pictures we just saw, where the material has come out and covered up the surface in a more diffuse manner. We estimate that this continual resurfacing of Io amounts to spreading a layer or blanket of volcanic material of about 1 millimeter thickness over the entire planet every year. Now that rate, if it continued over geologic time, would amount to essentially turning Io inside out.
Io is volcanic because of its location. It is locked between giant Jupiter, seen in this Voyager movie, and the other large satellites which can be seen orbiting around. raises a tide in Jupiter's huge atmosphere in exactly the same way our moon raises a tide in the Earth's ocean. The gravity of the moon pulls on the seawater of the ocean, drawing it into an oval-like shape. Because the Earth is spinning, this oval is swept forward so that it always points ahead of the moon. Also, the gravity of the oval itself accelerates the moon forward, pushing it out into space. Thus, the tides are gradually throwing the moon out away from the Earth. This is exactly what Jupiter's tides would like to do to Io, but Io's orbit and that of Europa and Ganymede are locked together. Io is held in place and is alternatively pulled and stretched by the immense gravity of Jupiter's tide. The heat of this constant deformation has melted its interior.
When Galileo looked at the Jupiter system, he saw that there were small bodies that were circling around it. And that was the first proof of the fact that everything didn't rotate around the Earth. His technology was a real breakthrough in thinking, and in just a few minutes of observation, you could see the little bodies going around Jupiter, and that changed the perception of the time. Voyager has given us a new view of the Jupiter system also. We had been convinced that the size of the body dominated its personality or dynamism. And now we know that its position in the system has even a stronger effect, so that small Io is very dynamic because it has a neighbor of Europa and its big neighbor of Jupiter. And that combination of things makes it an internally dynamic body.
Io is just a thin crust of sulfur and rock sitting on a ball of molten lava. Its volcanoes are powered by sulfur dioxide, boiling under the surface at minus 300 degrees centigrade.
The concept of something boiling at 300 degrees below zero or so is difficult perhaps for most people to imagine. And what we have here is, just to demonstrate this, is water and liquid nitrogen, which like hot rock and water on the Earth and like sulfur and sulfur dioxide on Io, differ in their boiling point so much that whenever they mix together, there's an explosive eruption. In this dewar, we have some liquid nitrogen at a temperature of about 350 degrees below zero is already boiling. And when we warm it by putting it in contact with the liquid water, it explodes into a cloud of steam. The result is a massive expansion of gases below the crust of Io, resulting in an exhaust, much like the exhaust of a rocket engine through a pipe up to the surface, in which the gases expand and violently erupt into the air.
These Voyager pictures show Io's vivid colors, but could they all be produced by simply the sulfur of the volcanoes?
On Io, at very, very cold temperatures, this yellow sulfur is virtually white. What we'll do is heat this gradually. Now you can see the color starting to slowly change. This is the next form. It's an orange form of sulfur. If we were to cool this very rapidly, this sulfur would retain its color. As the sulfur continues to change, it becomes redder and very liquid. So some of the flows that we see on Io, which are orange and red, suggest that this very runny form of sulfur froze, retaining the color. As we go to higher temperature now, the sulfur changes again to a deep red and becomes much more viscous, like syrup. It runs much more slowly across the surface, forming cliffs on the flow front.
Some of the sulfur spewing out of the volcanoes escapes from Io altogether. It remains trapped in Jupiter's huge magnetic field, which is 10 times more powerful than Earth's. Although invisible to the eye, this structure, the magnetosphere, extends out beyond the orbits of the 4 Galilean satellites. What you are hearing is the sound of radio waves generated by the charged sulfur particles trapped in the magnetosphere. Only the Sun, which we see here, has a more powerful magnetic field. Voyager carried an audio amplifier, something like a car radio, to listen to these changing radio emissions. This is Amalthea, another moon of Jupiter. Only 300 miles across, it orbits round Jupiter even closer in than Io. Its red color probably comes from Io's volcanoes. From Voyager data, 3 new moons have been discovered, all small, like Amalthea. This bright streak is a time-exposed picture of Jupiter's 14th moon, first noticed by a young graduate student. This black spot on the left is the 15th moon, seen very close to Jupiter with its shadow below it. Most unexpected of all, Voyager discovered that Jupiter, like Saturn, has a ring. Here it is seen backlit by the light of the sun.
We really hadn't expected to find a ring at Jupiter. All the calculations told us that such a ring should have long ago dissipated, but the fact that there is one tells us that there must be some constant replenishment of that ring.
But Jupiter's ring can hardly compare to the rings of Saturn, the next stop on Voyager's grand tour. After traveling another 500 million miles, Voyager's next task is to send back information from Saturn.
Okay, Charlie, let's see the blue filter version here first. All right.
At JPL, scientists have only begun to analyze the new information coming from Saturn.
Even at this point, it's easy to see the Cassini division all the way in front of the planet and the Encke gap.
Dr. Torrance Johnson, a member of the imaging science team at JPL.
Well, we're hoping to see new things in at least 3 areas. In the atmosphere of the planet, we're expecting to be able to investigate the meteorology of the weather of Saturn and to compare that with Jupiter. We're expecting, as we get higher and higher resolution pictures, to be able to see features in the atmosphere of Saturn which we cannot see at the resolution we have in the early stages of the observatory phase. We're also going to be investigating the detailed structure of the rings, trying to understand what they're made out of and perhaps how they formed and what causes their the gaps and the bands to appear in the rings. Then we're going to be investigating the entire satellite system, the weather on Titan, trying to investigate the thickness and depth of that atmosphere, whether there are clouds in the atmosphere, and investigating the surfaces of the other satellites, which are icy satellites with of a slightly smaller scale than the satellites of Jupiter, and we're interested to find out how they evolved compared to the satellites of Jupiter.
Saturn lies 10 times further from the Sun than Earth, and although it's also 10 times larger, it's so light it would float in water.
Saturn is primarily composed of 2 elements, hydrogen and helium, with about 10 times as much hydrogen as helium. This reflects the composition that we find in the Sun and in the other stars, and that we think may be left over from the original solar nebula that condensed to form the entire solar system. We also find smaller amounts of methane and ammonia and a trace of ethane, another carbon-hydrogen compound. Its internal structure remains poorly defined, but we doubt very much that there is any solid surface. Instead, there's a very thick atmosphere, and we have a little chart here that shows the uppermost layers of that atmosphere. Near the top, we think there's a smog layer, small particles that are created by photochemical reactions in the upper atmosphere, much like those that create smogs over the cities on the Earth. Farther down, there seems to be a thick layer of ammonia cirrus, and that's really what we see when we look at pictures of Saturn. Below that, there may be layers of colored clouds.
Saturn's rings remain the most arresting objects in the solar system. Galileo probably saw them first, but in his primitive telescope they appeared to be unmoving starlets on each side of the planet, and he was astounded when after a few years they disappeared. This mystery was resolved when better telescopes could work out Saturn's cycle around the Sun. At certain times, the rings are invisible from Earth. It was only in 1656 that the Dutch astronomer Christian Huygens concluded that Saturn was surrounded by a ring. Even then, it was thought to be solid. It was 2 centuries before it was understood that there were several rings and that they must be made up of particles. Yet the rings are huge. The widest one is 20,000 miles across.
The particles that make up this ring are much, much smaller than that, of course. Most of them are certainly less than a kilometer, but they may be tiny little particles of dust. We know that some of them must be coated with ice, with plain old water ice, and some of them may in fact be icy snowballs. We think the ring formed at the same time that the planet formed, from material that was near the planet, close enough so that it couldn't contract together to form a satellite, but instead remain dispersed because the gravitational field of the planet dominated the gravitational field exerted by the little particles on one another. Farther out than that, we can have satellites. But at that point, we have a ring.
Beyond its rings, Saturn has an extensive satellite system. These artists' conceptions show Saturn as it might appear from several of its moons. As many as 18 have been sighted, only about a dozen have been confirmed. Recently, 2 moons in the same orbit were observed. If this is a fact, it would be a unique arrangement in the solar system.
The 2 moons in the Saturn system that pique our interest the most are called Iapetus and Titan. Iapetus is intriguing because one side is 7 times brighter than the other side. No other moon in the solar system has that great a contrast. We don't really understand the difference yet. That's one of the things the Voyager is going to be looking at. The second moon is Titan. The satellite itself has such a low mean density that it can't be a rocky object, but instead it must be mostly ice. It must be a satellite rather like Callisto or Ganymede in the Jupiter system, about the same size as those 2 also, which means it's bigger than the planet Mercury, big enough to retain an atmosphere, and far enough from the sun so that that atmosphere will remain stable over the lifetime of the solar system.
Titan is the only moon to have an atmosphere, and is less cold than expected, about minus 160 degrees Fahrenheit. The surface may hold liquid nitrogen, possibly boiling or erupting with hot springs or geysers. Like Saturn, it probably also holds the same abundances of elements present when the solar system was formed.
In the case of Titan, those abundances have been modified because the hydrogen and helium have left. Nevertheless, the planet has retained the kinds of chemical conditions which we think, some people think, could have existed on the primitive Earth. And therefore, Titan may offer us a kind of natural laboratory where we can see the spontaneous chemical reactions taking place today that took place on the original Earth, the early Earth, that ultimately led to the origin of life.
So on one of Saturn's moons, there may yet be some chance of finding other life in our solar system. Voyager will continue on to approach Saturn itself. It will pass underneath the rings at a distance of only 84,000 miles. Nine months later, Voyager 2 will arrive and will make its passage through the Saturn system. Voyager 2 may then be programmed for the still more distant planets, Uranus and Neptune. Then both Voyagers will leave our solar system to begin the longest journey ever, a journey that could possibly last 1 billion years. Perhaps in all that time, they may yet again come to rest upon a friendly shore.
Mankind seems to have a great lust to discover the origin of life and where human beings have come from and how they have developed and how they have come to be where they are. And what we have found is that we can't answer those questions by just studying the Earth itself. We have to move away from our own planet and study the other planets in our solar system.
When Columbus stood on the shores of Europe and looked across the Atlantic, everybody thought, he was on a foolish quest. Who knew at that time that the great things that have happened on this continent would have taken place? So we are like the modern space explorers are like Columbus. We are looking out there Who knows what might come out of all this? One single word from a civilization beyond there, eventually, that kind of communication might be of great importance to us here on the Earth.
A billion years from now, that spacecraft will still be moving among the stars, bearing this record. And on this record will be a record of who we really were, and perhaps the best part of ourselves, our music. Long after there are no records playing on Earth, there are no more crickets chirping, there will be the sounds, the essence of who we were.
Hello from the children of planet Earth.